Yeah, I'll talk about the construction of a wave sequence for solid fuel adiabatic in-situ combustion in porous media. We have these main collaborators for this work, Akutlu from Texas University, Alexei, John Marchesin, Grigori, and Professor Breuning. So the outline of presentation, I put the main assumption of the model, the equation, the dimensionless equations. We talk about the non-combustion waves, the combustion, and analyze them as a traveling waves. I'll discuss about the Rantino-Gunio condition for these combustion waves. And present the wave sequence in two situations. Where ahead the combustion front, we have an oxygen-controlled case. There is a lack of oxygen. And the other one is the temperature-controlled case. So the main assumption is that we are working with a one-dimensional flow, a local term equilibrium. We use the ideal gas law, constant conductivity, heat capacities, etc. So it's a simplified model. We consider no heat loss, dominant rock heat capacity, and a small pressure gradient. So we assume that we are inject air in a porous medium containing some fuel, like oil or coke, and the target is to consume this fuel. Some notations: the porosity of the medium, the fuel density. Here is the fuel conversion depth. It means that if eta is 0, there is abundant fuel, and if eta is 1, there is no fuel. Temperature, oxygen concentration, the gas flow rate, pressure, densities, and so on. So the balance equations, let's say energy equation, the oxygen mass balance, gas, fuel, where this term, the source terms, is given by the Arrhenius laws, given here, and the ideal gas equation. So consider that assumptions, and the model, after some simplifications, the dimensionless equations are given by this system of 4 equations, where A is this value here. And remember that this is the okay. Here is the Arrhenius law for the reaction rate. Remember that, okay, phi is, we have this exponential factor here that models the reaction range. All and everything here are constants. So in the hyperbolic framework, consider large times and long distance, we can neglect these terms of second derivatives. And there is no combustion, so phi is 0. And using the ideal law of gas, right here is rho theta equal 1, we eliminate the densities, and the system is reduced to this one. And we have the 3 characteristic speeds, that is one immobile wave, a thermal wave, and gas composition wave. All of them are contact discontinuity. And what we would like to do is to put together this wave with these speeds together with the combustion wave. So now it's about the combustion wave. So we see the combustion wave as a traveling wave, and so we use this moving coordinate system where v is the combustion front speed. And in this variable, we have ddt is given like this and this one. And using this equation to eliminate holes, we get to these equations here. So the boundary conditions for a system is that behind the combustion, there is no fuel, which means that eta is equal 1. It's a fuel deficient case. The temperature has to be determined, and V also have to be determined. Ahead, the combustion will have two cases. That is, so the complete oxygen consumption, okay, Y is 0, there is no oxygen, there is abundant fuel, and also we have to determine theta, the temperature, and the Darcy's velocity. And in the temperature control case, ahead, the combustion will have the ambient temperature that I consider as 1, and we have to determine we have oxygen and abundant fuel. U is burned and U is unburned. So how can we analyze the traveling wave? So we integrate the system and obtain these, we integrate the PDE system to obtain this ODE system together with these constraints for V and theta. And how to put together the conditions ahead and behind the combustion wave. So at minus infinity, the previous first order, if we do this, we get the systems depending on theta, V, and Y, and eta. Remember that, okay, the burned means that eta B is 1, and the unburned we can have the controlled temperature case or the oxygen temperature case, controlled temperature case. If you analyze that Rankine-Virgouniod equations, and we have two parameters that we introduce these scaled combustion speed as the fraction of the combustion speed and the gas composition speed. And here I'm considering in the unburned region. And so we get the burned temperature as a function of the unburned one, and this scaled combustion speed. And analyzing this equation, we obtained two possible situations. We said, okay, this means the temperature burned in the burned region, we can have the burned below the unburned temperature or above one. We will consider this case. It means the upstream combustion we have. And for a fixed unburned temperature, we get this value. It's a maximum. Doing some calculation, we get this expression that's the maximum temperature, where there are no resonance between the hyperbolic waves and the combustion wave. We will consider this situation. And for the oxygen concentration, from equation 2 of the Rankine-Virgouniod conditions, we get the oxygen as a function also from theta unburned and this scaled velocity, And also we have two possibilities. Analyzing this graph, we have two possibilities for the concentration. For fixed temperature, unburned, in the unburned region. And after some analysis, we have the ranges for our parameters that is represented in that graphs. And we can have the sequence of waves. So, okay, we can have immobile wave, we inject, this is the injection conjunction, and we have the immobile wave, a temperature wave after the combustion wave, and the gas composition wave that can happen or not. This is the data, it's the production condition, this is the initial condition. So we have to determine all these quantities, and Vp and Yu may be given or not, depends on the situation or the case we are considering. So the first case is when we consider oxygen deficient case ahead the combustion front. This is the ambient temperature, and here this means that it's a field deficient behind or in the burned region. And we get, okay, this sequence. We can determine all speeds and the constant states that define the wave sequence. This is the theorem. The proof is only to calculation to obtain every quantity. And in this case, since Yu is 0, there is no oxygen, it does not appear this wave here. And the second is the temperature control case, and theta U is 0, but Yu have to be determined. But in this case, if we analyze as the ODS system, we can see that, okay, we have no equilibrium for the system if we consider the original Arrhenius law. So we have to do a modification in this equation, in the Arrhenius law, since this state is not an equilibrium. And we use the cutoff Arrhenius law, doing something like this. So since the reaction is too small near the 0 temperature, we fix that, okay, for theta less the ambient temperature, there is no reaction. But really, here it's only approximation. It's a mathematical approximation for since U is not the equilibrium of system. If we do this, we have this equilibrium, and we have the combustion wave, and also we can determine all the sequence and all the speeds of the hyperbolic waves and the combustion wave. And here we get this gas composition wave. Okay? And we can do all calculations. So here we have the speeds. And certainly, if we got Yu 0, also we have the gas composition wave. The gas composition wave. So some reference about this work. It's the system originally it's obtaining the states of Aquatlo, and here there are some works that we did together about this stuff. Okay, so I think that's all I prepared to say. Thank you.
Any question?